So it's a fairly basic idea. We spent an awful lot of time yesterday explaining why this is the case. But in the end, when you're talking about sums of functions, all it means is you're adding the two functions together. And the order doesn't matter because the order of addition is not relevant. When you add things, 4 plus 8 is 12. 8 plus 4 is still 12. The same holds true with functions. However, when you're subtracting functions, f minus g, quantity of x means, f of x minus g of x, and order is important there. We have this domain rule, which we're going to continue into today when we talk about products and quotients of functions, except there'll be a little twist for quotients of functions. But the domain rule basically says that the only way you can add two functions together, or the only way you can subtract two functions together, subtract two functions from each other, is if they both exist. And when we talk about their existence, we're talking about xy's. So if you have both functions that you're going to add, but one of the functions doesn't exist in a particular region, it's missing that domain, then you can't add it to the other function. So the domain rule simply says whatever the common domain is to both functions, that's the domain of either the sum or the difference. But the range, and this is an important point, the range can only be found, only as a pretty severe word, but it will do for now. The range typically can only be found by graphing the new function and looking at the graph. There's no simple way to do it. What this culminated in yesterday, and this is what we spent a lot of time proving or demonstrating, is that really it's all about y coordinates. So when I'm talking about f plus g of a, where a is a specific number, all that means is figure out what f of a is, figure out what g of a is, and add the two. But you should know f of a, listen very carefully to this, f of a is just a way to say the y coordinate on f when x is a. That's all f of a is. It's the y coordinate on f when x is a. And g of a is the y coordinate on g when x equals a. So you add the y coordinates and the order doesn't matter. If I had f minus g quantity of a, then we subtract the two y coordinates or y values, and the order does matter. One final note here. If you're looking for the y values or coordinates to add or subtract, there's a whole raft of ways that you can find them. Maybe you're given the equations of both functions, so you can calculate each y coordinate. Maybe you're given a graph, like question 6, I believe, where if I said to you, what is f plus g of 4, that simply means f of 4 plus g of 4. So what you're going to do is look at x equals 4 and read the y coordinate on f. The y coordinate on f is 5. So that means f of 4 is 5, plus you're going to read the y coordinate on g. Get in there. There we go. And you can see that the y coordinate on g is 3, so it's 5 plus 3. So you may extract those numbers, those y values, from a graph. They may be given to you in a table of values. They might be given to you indirectly because, we're looking at the bottom of the screen here, they might be given to you indirectly because you have equations that you need to put the x coordinate in to pop out those y values that you have to add or subtract. And that is it in a nutshell. So can you take a minute, please, and take a look over your work and see if you have any questions you would like to ask me. And you're told h of x. So I want to make sure you understand something here. In this question, h of x is equal to f of x minus g of x. Correct? Okay. And in every question you did leading up to question 11, I gave you this and this was given, and you had to find h of x. You would subtract the two functions. The difference here is that you're not given g of x, you are given h of x, and you are given f of x, and you are asked to determine g of x. Good? So what we can do is we can just put this in here. We can put h of x in. You said c, am I right? So I can put negative 3x plus 11 in for h of x. F of x, we're told, is 5x plus 2 minus g of x. So we're going to solve this equation for g of x. G of x right now, Shesmaida, is on the right-hand side and it's negative. So I'm going to add it to the other side where it becomes positive g of x. I'm going to move everything else to the right-hand side, so I will get 8x minus 9. Does that make sense? Okay. Can I ask you a question? When you did maybe A or B, did you just look at A and B and figure out what it had to be by just looking at it? Yeah. So as soon as you have multiple terms, that just by inspection figuring it out doesn't work. And this way we have an algebraic method. And you could have solved A and B and even D like that as well. Okay. All right, let's move on. We're going to be looking today at products and quotients, so I believe this is on page 13 of your unit handout. And I guess what I would say to you is what we are doing today is everything that we did yesterday with sums and differences. Okay? So calculators down, focus on the handout. We're going to be sketching the graph of functions that are either products or quotients. We're going to be determining domains and sometimes ranges of products or quotients of functions. And of course, finding equations. I want to review something with you though, and these 4 words in math are very important. These are your 4 basic mathematical operations. So what does the word sum mean? I think you know this. You don't need a review of it, but I'm going to do it anyway. It's the result that you get when you add things together. And the order when you add things together is unimportant. It makes no difference in the answer. Shouldn't use the word difference. It doesn't affect the answer. The word difference is the result of subtracting, and the order in which you subtract matters. A product is the result of multiplying, and order is not important, but a quotient, order is important. A quotient is the word we use to mean the result of division. So 100 divided by 50 is 2. But 50 divided by 100 is not 2. It's 1 over 2. So order matters when you're dividing. There's one other thing I want to talk about here. As long as the numbers that you're adding exist, then the sum will be defined. What I'm kind of getting at is if you have 2 functions and they both exist in a certain region, you can add their y coordinates. You're allowed to. No question about it. The difference of 2 numbers, as long as the 2 numbers exist, are always defined. Okay, if I write down one number and you write down another number, no matter what, it's possible to subtract them. Again, as long as they both exist. You know, if one of the numbers doesn't exist, then you can't add it or subtract it. The product of 2 defined numbers is always defined. But the quotient is not always defined. Just because you have 2 numbers that you want to divide doesn't mean you're allowed to. When are you not allowed to divide? What am I talking about here? Jonathan? Right, I am not allowed to divide by 0. So when I have A plus B, as long as A and B are both defined, I can add them. When I have C minus D, as long as C and D are both defined, I can subtract them. If I have E multiplied by F, as long as they're both defined, I can multiply them. If I have G over H, I am not always allowed to divide them because H is not allowed to be 0. And that's why Jonathan said the denominator can't be 0, because that's what division involves. All right, let's take a look at the notation first of all. The product of two functions can be written as h of x equals, now there's a solid dot in between the f and the g, but we pronounce it as f times g of x. And what it means is f of x multiplied by g of x. Before we go on, it's really important when you draw that dot to draw it as a solid dot, because these two things mean something different. Okay? A solid dot means a product. An open dot means something different that you haven't learned about yet, but we're going to start talking about tomorrow. So it's very important that you pay attention to how you write this, particularly on a written response. Notice that f times g, quantity of x, is the same as g times f, quantity of x, because multiplication is not an order-sensitive operation. Multiplication is the same regardless of the direction you go. The quotient of two functions is written as f over g of x, and it means f of x divided by g of x. And that's just notation. So note that f over g of x is not equal to g over f of x, because f over g of x means f of x over g of x. G over f of x means g of x over f of x. There's a lot of letters in saying this stuff, so you have to choose your words carefully. These are reciprocals of each other. They're not the same, though. Go ahead, Ian.
In the previous lesson, we learned that, well, it was shown that you could have like f plus g quantity with the x on the outside, and you'd assume that you'd multiply in the x.
You're not multiplying in the x. It's not a multiplication. It's not a multiplication. So all it means is it's just a way of writing f of x plus g of x. And I think I even said you're not multiplying something through. It's not that kind of operation. It's just a different language. Okay. Have I cleared up any question you have? Okay. All right. So let's put this into action. First of all, domain rule. I told you that the domain of a sum or a difference of two functions is the domain they share in common. And I think you really need to have that clear in your head as to what we're talking about here. For example, if you have one function that is defined from negative infinity to infinity, okay, this is x. And maybe this function here is f of x. And you have a second function, but the second function is only defined from, we'll put a number on here, 4, including 4, because I have a solid dot there, to the left, and that's maybe g of x. Then what we would say is the common domain. I better not use red. The common domain would be where they overlap. And to me it's obvious, but I don't know what goes on in students' heads all the time. Do they overlap when x is 4? Well, yeah, because they're both there. And they overlap at x equals 4 and to the left of 4, which means the common domain would be x is less than or equal to 4. And that's what we talked about yesterday, if we're adding or subtracting two functions. Look, all I'm telling you is the same thing is true if you're multiplying or dividing, with an exception. Okay? So this domain rule is really the same as the rule for a sum or a difference. But because we're not allowed to divide by 0, the domain of a quotient has a further restriction, and that's that you have to exclude values of x from the common domain if they result in division by 0. Now think about this for a second. If f of x, if f over g of x means f of x over g of x, and we're saying g of x is not allowed to be 0, we're saying g of x is not allowed to be 0, don't forget g of x is just another way of saying y. Y is not allowed to be 0 on the function you're dividing by. And where is y 0? On an x-intercept. So any place the function we're dividing by has an x-intercept, that cannot be in the domain, because the y-coordinate there is 0. All right, for example, look at this graph. This is a graph given to you in question 6 from yesterday's work. And I've already got the domain of the blue function there. Let me put in the domain of the red function. The domain of the red function starts at -5 and moves to the right. So if I said to you, and you don't have to write this down, this isn't in your notes. If I said to you, what is the domain of f plus g? Well, you would say the domain of f plus g is x is greater than or equal to -5. Would you agree? It's common. F minus g, x is greater than or equal to -5. F times g, x is greater than or equal to -5. F over g, x is greater than or equal to -5, except you can't divide by 0. So we're dividing by g of x. Where is g of x 0? Well, g of x is 0 at -5, isn't it? So we can't have the equals to. It has to be greater than. What about g of x over f of x? Well, the common domain would be x is greater than or equal to -5, but we can't divide by 0, and f of x is what we're dividing by. And by the way, I see I shouldn't have x's in here because I have the x's outside. It isn't a special way of writing divisions. F of x is 0 here and here. So you would say that x is greater than or equal to -5, but x cannot be equal to, and let's just assume that those are plus and minus 1.5. Do you get my drift here? It's common domain, common domain, common domain, but as soon as you're dividing, you have to toss out non-permissible values. All right, let's get to work on the examples now. Look at these two functions. What's the domain of each function? So f of x is the square root of x minus 1. We've learned that you cannot take the square root of a number unless it's greater than or equal to 0. In other words, the radicand has to be greater than or equal to 0. We solve this. The domain of this function is x is greater than or equal to 1. G of x is x minus 2. There's no real work needed to discover the domain. Is x is any real number? Because it's a linear function, right? Linear functions go on forever in all directions. I don't think it's necessary for you to have to do this, but I will do it anyway. This is f. This is g. The common domain would be where x is greater than or equal to 1. By a show of hands, how many of you wouldn't need to draw that to see that? Okay, good. So the domain, that's the domain of each function. Write the equation of h of x equals f times g. Well, this is really simple. This just means f of x times g of x. f of x is root x minus 1 times g of x, which is x minus 2, and that's all you have to do. What is the domain of h of x? Well, it's the common domain. And let's graph this beast and see if that is in fact what the function looks like in terms of domain. So y is equal to the square root of x minus 1. Close the brackets and then multiply by, in brackets, x minus 2. Let's go zoom standard. And I will zoom in a bit so you can see it in a little more detail. We do have to contend with the limitations of your graphing calculator in terms of the graphics. There's a little bit of error between the x-axis and where that starts, but the fact of the matter is it does touch the x-axis, and I can prove it to you by going trace 1, and it's able to calculate a y-coordinate. Trace 1.05, it's able to calculate a y-coordinate. Your graphing calculator just can't cope with that with the steepness of the curve, essentially. Any questions with that first example so far? Okay, good. C, what's the equation of f over g? Okay, well, f over g would be k of x. This means f of x over g of x, which would be root x minus 1 over x minus 2. What is the domain rule? Okay, well, the domain rule is that x must be greater than or equal to 1, because that's the common domain, but, are you with us, Ian? But you cannot divide by 0, so this creates an NPV. And what we would call a non-permissible value prior to today, I'm just saying that's the further restriction in the domain rule. What's the common domain? And then, oh yeah, when are we not allowed to divide? We're not allowed to divide when the denominator function equals 0. So x minus 2 is not allowed to be 0. X is not allowed to be 2. So what does this mean? It means if you were to do a number line description of that domain, then it would there's lots of ways you can do this. X is allowed to be 1. It must be greater than 1, but it can't be equal to 2. That's what that's saying. So it's another way we could write this is you could say x is an element of 1 to 2, but not including 2, in union with 2, not including 2, obviously, to infinity. And we don't include infinity with a square bracket because infinity is never something you can actually achieve. Well, let's graph it and see what this thing looks like. And by the way, if you're wondering, our purpose here is not to be able to graph this from the equations, unless you're using a graphing calculator. So the square root, y equals the square root of x minus 1, close brackets, and then divide by, in brackets, x minus 2. I'll go zoom 6 again. Oh, well, there's an asymptote there, which makes sense, everybody, because look at this function. Look at this function. There's a factor on the bottom. It's not a rational function because of the square root. But there's a factor on the bottom that does not cancel. Oh, so that non-permissible value is an asymptote. It's just a weird situation because we are used to seeing something on both sides of the asymptote that goes up and down forever. And this beast starts here and goes down. And by the way, that's 1, right? That vertical line is not the y-axis. That's x equals 2. So x is greater than or equal to 1, but it doesn't equal 2. It works. I just want to check, does yours only go to C? Okay. I'm gonna throw this out though. What if that was f over g? What if I had g of x over f of x? Which would mean we would have y equals x minus 2 over root x minus 1. Ian?
Would it just be the top curve shifted to the left?
I don't know yet, but what I'm interested in here is the domain. So what is the common domain to these functions? Well, the common domain, we've already established back here that the common domain is x is greater than or equal to 1, right? That's the common domain. So if I said to you, what is the domain of g over f, you would start by saying x is greater than or equal to 1. And then you would say, but I need to take out of that domain any value of x where the denominator is 0. What value of x makes the denominator 0? 1. Which means, I don't think we want to write this. Is it wrong? No. But this is certainly more ideal. So what is this going to look like? Whatever it's going to look like, it has to start at 1 but not including 1, which is a weird idea that when you look at where it is at 1, it doesn't exist, but it exists immediately after. Well, let me graph it. So this time we're going to flip things over. I'm going to have x minus 2 over the square root of x minus 1. Zoom 6. Okay, it almost looks logarithmic, but it isn't. I'm going to zoom in a little bit. So your prediction is kind of off. It's very difficult to look at these things. I'm going to get rid of this because it doesn't apply here. It's very difficult to look at this function and say, I think I know what it's going to look like. It's not easy. I'm going to zoom in around a bit. Let's do this. So if I were to go trace 1, there's nothing. There's no y coordinate. If I go trace 1.0002, there's a y coordinate. Is that really what the y coordinate is? Negative 70? That seems odd. Wow, you know what? I think there's an asymptote there. I think that's an asymptote. Even though it's under a square root sign, I guess it is a factor that doesn't cancel. So this thing has an asymptote there. It isn't even a square root function like Ian, you and I think both thought it would start at a point and go up. It doesn't. It's asymptotic. Okay, let's take a look at number 2. Given those functions, what is the product of them and what is the domain and range? So the product, h of x, is going to be f of x, which is x plus 2 squared minus 5, times g of x, which is 3x minus 4. And I hate to break it to you, but we're expected to simplify this. Okay? Which means we have to take that x plus 2 and square it. Don't forget that x plus 2 squared means x plus 2 times x plus 2. Which if we FOIL it out becomes x squared plus 2x plus 2x plus 4. Then we have that minus 5. And then we have to multiply by the 3x minus 4. So I'm going to clean up h of x just a little bit. X squared plus 4x minus 1 times 3x minus 4. We okay to that point? Okay. You know, this is the unfortunate thing. We have to spend our valuable Math 30-1 time doing a Math 10 problem now, where everything in the first polynomial gets multiplied by everything in the second polynomial. I need to take x squared times 3x, which gives me 3x cubed. I'm focusing on this right now. Then I take the x squared times the negative 4, and it gives me negative 4x squared. And then I say to myself, I'm done with that x squared. I've completed that contribution. And now I move on, and I'm going to look at the 4x. And I multiply the 4x by the 3x to get 12x squared. And I have a habit of stacking similar terms because I'm going to be adding them together. And then the 4x times the negative 4 is negative 16x. And I say I'm done with that, and I will check that one. 4x times 3x is 12x squared. 4x times negative 4 is negative 16x. Now I move on to this one. Negative 1 times 3x is negative 3x. Negative 1 times negative 4 is positive 4. So h of x, the product of these functions is 3x cubed plus 8x squared minus 19x plus 4. What is the domain of this function? Well, if you look at the original two functions, f of x is a quadratic function. It's a parabola with a domain of any real number because that's what parabolas have for a domain. G of x is a linear function. The domain of that is any real number. So the common domain is any real number. But you didn't need to do that because if you look at h of x is a degree 3 polynomial function. It goes on forever in both directions. Okay. Any questions with number 2? Ian?
What does the degree matter for? Because don't all functions go in infinite directions if they have a degree greater than 1?
All polynomial functions, yes. It doesn't matter. When I said it's a polynomial function of degree 3, I could have just said, since it's a polynomial function, even polynomial functions of degree 0 have a domain of any real number because they're horizontal lines. So there was nothing special about me saying degree 3 if that's what you were focusing on. Okay, number 3, f of x is x squared, g of x is root 4x minus 5. What is the product of the functions and what is the domain of the functions? When I started off today, I said we will be dealing with domain and occasionally range. I don't think the range in this question is that important, but I want to talk about it. So what is the product? H of x is f of x times g of x. We don't have nearly as much work cut out for us here. Because we can't really simplify that. We just multiply the two functions together. If you were to take a look at the domains, the domain of y equals x squared is this. The domain of root 4x minus 5, well, I guess we got to figure that out. 4x minus 5 cannot be negative, so it must be greater than or equal to 0. We solve that equation by adding 5 to both sides and getting 4x must be greater than or equal to 5, which means x must be greater than or equal to 5/4. So there's some mark on here of 5 over 4. And this is the domain of G. So G of x has this for a domain. So what is the common domain? Well, x is greater than or equal to 5/4. That's it. Which, I mean, you could have done just by looking at this. But x is greater than or equal to 5 over 4. Does anybody want to stick your neck out and guess? Tell me, figure out what the range is without using a graphing calculator? And as some of you are thinking more about this, I hope that that question drives home the fact that range is trickier. As we talked yesterday, it's not the common range. It doesn't work that way. I told you pretty much have to look at the graph, but in this case, you can figure it out without that. Arden? Could y be equal to 0? It turns out this will be the range. First of all, I can explain to you why y will always be positive. Forget about 0 for a second. You are in this function squaring x. So whatever x is, squaring it will become positive as its contribution to the function. And this is the principal square root, which will always be positive. So y will always be positive, and there's a possibility that y will be 0, because if x is 0, well, actually, x couldn't be 0 because that's not in the domain. But this thing could be 0. So an educated guess would be this. Let's graph it and just see. Y equals, what do we have? X squared square root 4x minus 5. And you know, if this were calculus, we could do derivatives and all that other stuff to find out what it looks like without this. But it's not, thankfully. I better go zoom 6. I think this kind of maybe suffers from, if we zoom in, the same problem as one of those other ones where your graphics are not that great. But I'll give it a crack. Yeah, that does go down. 4/5, by the way, is 1.25. If I go trace 1.25, it gives me a y coordinate. It's just so steep, my graphing calculator can't connect the dots. Okay, and final one, determine the equation of the function g of x over f of x. So h of x is g of x, which is 2x plus 6, over f of x, which is x squared plus x minus 6. Done, 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 done. Okay? Since it's a rational function, though, we really should state, and this goes back to chapter 9, which we just finished, the non-permissible values of x. And how do you do that? Well, you factor everything. And the bottom factors into x plus 3, x minus 2. And that means that x is not equal to negative 3 or positive 2. I don't know if you really need to write that when you write down what the function is, but on an exam you might see it. What about f over g? Well, that's just the opposite, isn't it? This time we're going to have on the top, this is for k of x, we're going to have x squared plus x minus 6 over, forgot what I had, 2x plus 6. If we factor that, it's x plus 3, x minus 2 over 2x plus 3. X is not equal to negative 3. So are we okay with A and B? Okay, so now C says analyze the two functions. What am I talking about? Well, we had a lesson where we analyzed rational functions by talking about x-intercepts, holes, asymptotes. When we take a look at, and I'm going to write my answers to C up here where I can see these. When I analyze this function in A, there's a hole at negative 3 comma something. There's a vertical asymptote at x equals 2. And how would I find, and by the way, there's a horizontal asymptote. I guess we can do that too. At y equals 0. Can somebody tell me why there's a horizontal asymptote at y equals 0? Maddie? Say that again?
The degree on the denominator.
Right. When the degree on the bottom or denominator is bigger than the degree on the top, then y equals 0 is the horizontal asymptote. How do we find the y coordinate of the hole? Ian? So, but that's the x coordinate. That's how we know it's at negative 3. What I'm saying now is how do we determine the y coordinate of the hole? Right. So take negative 3 and put it in every place there's an x that's left over. And I'll get 2 over negative 5. Negative 3 minus 2 is negative 5. So negative 2/5. That's your analysis of that. And finally, if we do an analysis of k of x, there is no horizontal asymptote. And Maddie, why is that? Right, it's opposite to the other one. So when the degree on the top is higher than the degree on the bottom, there's no horizontal asymptote. There is no vertical asymptote. The reason for that is the non-permissible value cancels. The only non-permissible value cancels. So we have a hole, and the hole will be at negative 3. It probably shouldn't come as a big shock to you that the y-coordinate of this hole is the reciprocal of the y-coordinate of the other hole, because the whole thing's upside down. But if you cancel this and put negative 3 in, you will get negative 5 over 2. And I will leave it to you. If you wanted to, you could graph each of them on your own time and see that that's in fact the case. So a little bit of a connection between what we're doing today and what we did day before yesterday or yesterday. Page 496, 1 to 10. You do not have to graph any of these. Remember, it's y coordinates. That's the bottom line. It's y coordinates you multiply. It's y coordinates you divide. It's just that when you divide by a y coordinate, that y coordinate can't be 0. So we're still dividing or multiplying y coordinates. So get started on that. Anything else I need to tell you? I don't think so. I think that's good. So get going, and I will come around and help you out.